Usually these course lessons are set up so that I spend one lecture going over a topic, and then we have a project which applies it. In this lesson, we'll be doing a project walkthrough to explain how to utilize actions in ROS 2. ROS actions are not inherently complicated, but they have a lot of parts to them, so it's easier to understand when taught in the context of using it in a robotics project. As you learned in the ROS 2 overview video, ROS actions is another inter-node communication method. Here, an action goal is similar to a service request, and an action result is similar to a service response. The feedback aspect of an action is similar to a publisher, in which it keeps publishing feedback relevant to the state of the goal until a result is reached. In this project walkthrough, we will program similar functionality shown in the ROS overview animation. The project scenario is that we have a mobile camera robot, and we want to send it to coordinates to a goal point to navigate to. While the robot is navigating, we want it to send feedback on how far away it is from the goal point. When it reaches the goal, the robot then returns a result of how long it took to get to that goal point. This is an ideal situation where we'd want to use a ROS action. It has a goal aspect, feedback aspect, and a result aspect to it. An additional thing to note is we will also need to create a publisher to simulate a position sensor which tells us the current point the robot is at. Our action will find the distance between the goal point and the simulated current position to send feedback on how far the robot is from the goal. Okay, now that you understand the idea behind this project, let's walk through it together. Alright, so how do we go about creating a custom action interface? Well, it's quite similar to how we create our service. First, we need to create a custom action file. This will be placed in a folder in our package called action. Then I will call my new action file navigate.action. There are 3 sections to this file, and I will quickly comment out here and make this file more readable. The first is goal. Just like services, we will separate each section with 3 dashes. The second section is the result, and the third section is the feedback. My goal for this project is a point which I want the robot to travel to. I will do this project in terms of a grid with X, Y, and Z coordinates. Rather than creating a custom X, Y, and Z part to my request, I can do a quick search to see which ROS message types are available that may be able to help me. So here this simple search takes me to the Geometry Messages ROS Wiki page. So the ROS Wiki page is the old wiki meant for containing information about the ROS packages, but nonetheless we can utilize this for some information. And so here we actually see a point ROS message type, and if I go and click on it, we can see it contains 3 attributes in X, Y, and Z, just like what we were looking for our navigate action. So it makes sense to utilize this already created message type instead of creating our own. To include this in my action file, I can simply type geometry messages /point, then I will name this attribute of my goal point. My result of this action will be the time that elapsed while I traveled to the goal point. I could use one of ROS's time-based messages, but I will keep it simple and just use a float32 message type to return back the elapsed time in seconds. Lastly, my feedback will just be the distance my robot is from the goal point. I can also keep this simple and just use a float32 message type to return back the distance in meters, assuming that my grid I use is in meters. Great, that's all we need for the action file. But we need to make sure our package is set up to create a custom action interface. So I'll go ahead and save this file, and if I open up my package.xml, I already have most of the dependencies I need from the services lecture related to creating custom interfaces by including ROS IDL. The only additional thing I need to add is the dependency to action messages and the geometry messages package like so. That's it. I can save this file and close it. Now I'll have to head over to my CMakeList text file to let it know that I made a new interface and it needs to compile. All I need for this is to add the file to my ROS IDL generate interfaces function. In this case, it is action/navigate.action. One thing to note is that I use the geometry messages library for my goal point, And I'm using the action messages package so that I can create these custom action interfaces. So I need to make sure that it's included as a dependency. And in order for the dependencies to be included, I also need to be able to find the package. So I'll create those declarations up above as well. All right, with that, I can save the file. So as usual, I can head over to terminal and go over to run build task. But as I mentioned before, I'll be using the Control-Shift-B shortcut when running my compilation. All right, so here we see my workspace compiled successfully. So I'll go ahead and close this, and I'll close my cmakelist.txt file for now and open up a terminal. Change into my workspace. Source it. And now if I run the ROS2 interface list command, we can see under the actions subcategory, we see the custom navigate action, which I just compiled. Now there's one more thing that I would like you to see, which is the ROS2 interface show command, and use it to show our new action from within our package. So here we see what we wrote down in our action file, as well as the full X, Y, and Z attributes of the point message. Great, now let's go ahead and create our action server and client nodes. So I'll go ahead and minimize this and create a new file in our source folder, and I'll just call it actionserver.cpp. As usual, I can include the ROS client library header files as well as the RCL action header. Then I will include our custom navigate action interface header. I'll probably want to shorthand this when I use it later, so I'll make my typedef statement and call this navigate action. Another data type we will be working with frequently is the server goal handle object from the RCL action library. Oh, and it seems I made a typo here where I meant to put .hpp instead of a /. So this server goal handle will be based on the type of our custom action, so I will configure it as such. And I will just shorthand all of this to goal handle. Now naturally all C++ files need to have an int main function, so we should go ahead and set that up, which will simply initialize ROS communication, spin a shared instance of our node, which we will be making, and then shut down the ROS communications. So let's go ahead and create this navigate action server node class. Go ahead and set up the constructor. And as usual, I need to set the tabs for this file to 2. And the first thing I will do is create an attribute of the class which will hold my action server, which I will do in the private scope. This uses our custom action interface as a type. Then back in my public scope, I can assign this variable to the RCL CPP actions create server function. So this will take in the node which the action server will be registered with, so I'll just pass it this. Then I pass in the name of the action, which I will call navigate. And here we see VS Code tells us possible input arguments, which in this case, the next argument will be a function which handles the goal that gets sent by the client. So I'll just bind a method of our node called handleGoal. This will take in the class and 2 other arguments, which will be the goal UUID and the goal message itself. So I'll declare 2 placeholders. You could declare the placeholder namespace here if you wanted to in order to shorten the code, but I'll just leave it as is. We will create this function in a bit, but for now, let's finish up this action server declaration. So the next argument will be a function which handles action cancellation requests. So this will take in the goal handle, but again, I'll be using placeholders, so I can just copy the line above and use only 1 placeholder. Then the last argument will be a callback function, which handles processing the goal if it gets accepted by our handleGoal function we defined earlier. So I will call this method handleGoal, and it takes in the node and placeholder, which will be for the goal handle input. Great, with that, we now have our action server created, so let's create all of these callback functions. So the first is our handle goal callback, which will be of type goal response. This will take in the UUID and a shared pointer of the goal attribute of our navigate action interface. You will get to see what this UUID is later. For now, I will just cast it as void, just so we don't get a compiler warning saying this variable is not used. Then for the time being, we could go ahead and print out all the attributes of the goal so we can properly see that the server retrieved it. Remember, we have to get the goal point field name we defined in our custom action, then we can get the individual X, Y, and Z attributes of the point message. Then lastly, I need to return a goal response, which basically works as an enumerator for returning a status. So in this case, I will return accept and execute. You could also return reject or accept and defer. And here's an image of the documentation explaining each possible return statement. Oh, and it seems I forgot a semicolon at the end of our class declaration, so I'm going to put that in before I forget. But basically, within this function, you could do some inspection of the goal to see if it's valid, and if it's not, you could reject it, or maybe you only want to process one goal at a time, in which you could defer it temporarily until you finish the other goals in a queue. Keep in mind that the accept and defer message is just a courtesy to your client. This constant does not affect at all how your code works, so you need to program in your own deter or queue functionality. Only rejecting a goal will make it so that the goal does not trigger your handle accepted callback. Next up, we'll create the cancel response callback. This takes in the goal handle, so we'll go ahead and utilize that type def we created earlier to shorthand this. Again, for now, I am not going to utilize the goal handle, so I will just void it. I will, however, make a printout stating that the goal has been cancelled. And I will go ahead and return an accepted enum from the cancel response class. As you can see here from the docs page, this can be either accept or reject. Now again, this enumeration return is just a formality. It is up to you to make the functionality within your class to process a cancel request. But with that, let's move on to the last callback, which is responsible for processing the action goal once it's been accepted. This also takes in the goal handle, like our handle cancel method. Now normally this would be where you put all your code to process the action. However, you want to do it in a non-blocking way to make sure the rest of your node can continue to function and pull the ROS operations executor. So what we will do instead is create a new thread for another method of our class, which will actually be responsible for properly processing the goal in another thread. So it'll be similar to this function in the sense that it takes one attribute, which is the goal handle. So we need to specify a placeholder when we call bind, and then later in the thread parameters we can pass in the actual goal handle. Lastly, we can go ahead and detach this thread from the current process. So I know it's a weird layout, but that's just because there are other ways which you can have organized your code, especially in a non-object oriented or distributed manner, in which you may not have to do as much binding and threading. For now, let's go ahead and create this new execute callback, which will be in charge of processing the goal, publishing the feedback, and once we are done, publish the result. I will make a print statement saying that we are beginning execution of the goal just so we have some feedback in the terminal. Then I will go ahead and set up my goal, feedback, and result instances. So first off, we will get the goal from the goal handle, then initialize our feedback message, and initialize our result message. Both of these will need to be pointers in order to be processed correctly. Alright, and just as a side note, my linter got stuck there thinking that something was wrong or something was misspelled or didn't exist. I had to actually restart my VS Code. I think it was bugging out because of the recording that was happening in the background. Nonetheless, this is the same code I left you off with. but now we don't have as many squiggly line errors. So, heading back to our execute function, let's recap what this action is actually supposed to do. We have this goal, which has some coordinates, and we want to calculate the distance from that point to our robot's current position. So, how do we even know where our robot is? Well, I will need to make an attribute of that within our class. In this case, I will just use the point data type from the geometry messages module and set it to a variable called robot position. Now this data type is really long and we're going to be using it quite a bit, so I will go back to the top and shorthand it so I can declare it as point. So now I can just shorthand this message as simply point, which I've already done. Now you may have noticed we never explicitly imported in the geometry messages package header files at the top, but we don't get any errors. That's because our custom action depends on geometry messages, so it's already been included, but you could feel free to include it if you wanted to. Anyway, back to our robot position point. I will go ahead and initialize it within our constructor like so. Now this takes in an X, Y, and Z attribute, but they will default to 0 when you initialize, so I'll just leave it as is for now. Then we have to be able to somehow update this position. Well, on a real robot, we would have this point value being published from some type of sensor node, so I can make a subscriber which will retrieve those values. You could have made this a service or some other method to communicate that the robot was moving, but generally a publisher-subscriber architecture would be used for this kind of functionality of retrieving positional coordinates or sensor values of position. But now I need to make sure to define this variable, which I'll go back in the private scope. So it'll be a subscription object which uses the point as its type. Now I know it's been a while since the subscriber lecture, but I'm sure you remember that this function takes in the topic name, which I will call robot position, followed by the quality of service, or an integer to represent the queue, so I'll just make mine 10. Then we need to declare a callback function to run every time a new message is received, which I need to bind, and I will call update robot position. This will take in a placeholder with the point message received. So let's go ahead and define another callback function for this subscriber. And all it's going to do is set the robot position attribute equal to the value received from the message. That's it. Okay, with that, our code is now able to keep track of the position of the robot, which we needed to calculate the distance from the goal point. So let's head back to our execute function above, which we were originally working on, and finish that up. So here I can take the feedback message and point to the distance to point attribute I defined in the action. Oh, is my tab size incorrect? I don't know what happened here. Let's go ahead and set the tab size to 2 to fix that up. And we want to set it equal to the distance, which we can calculate by using a standard vector length equation, which you may recognize since it looks like the Pythagorean theorem, in which we take the square root of the difference of each initial direction and the goal point. If you have questions about this, just look up how to calculate the distance of a three-dimensional point online. But now that I've calculated the distance, I want to publish the feedback. So I can do that like such. Now, the only problem here is that I want to redo the calculation and keep publishing feedback periodically instead of just once. So I'll need to put all of this in a while loop. Basically, I want to keep looping until we reach the point, or essentially when the distance is equal to 0. However, in most professional cases, you may not exactly reach your destination perfectly, so you may just set a distance threshold, which basically states that you are close enough to that goal. So I'll go ahead and put all this contents within the while loop. And now I can go ahead and define this threshold. For now, I'll define it at the top of the file. You could have felt free to make this a part of the node class, such as a configurable parameter, but for this lecture, I think we got enough going on as it is, so I'll just try to keep this simple. So let's go back to our callback function. Then I need to be sure to initialize this feedback distance to point prior to the while loop. So I'll just initialize it as the distance threshold for now, which will trigger the while loop to at least loop once. Now within this while loop, you'll notice we have no delay. So it's going to keep recalculating the distance and publish the feedback as fast as it can, which is not very desirable. So I can set a delay using a ROS rate instance, which I'll define the while loop like so. So 1 here means I have a rate of 1 per second, aka 1 hertz. Then at the end of my while loop, I can call the .sleep method, which will enact the delay. Great, with that, the while loop is finished. So let's move on to sending back the result once we've finally reached the distance threshold to the goal point. So our result takes in the elapsed time it took to process this goal. One of the ways we can do time management is with the clock attribute of the ROS client library using the now method of it. Great, now I can subtract it to get the elapsed time. And it seems I made a typo here on clock. Okay, this seems good, but now we have to actually define when our start time was, which I will do right after we print out our executing goal message. Okay, so now that's defined, but notice it says it doesn't know how to resolve duration. Well, that's because when we subtract 2 clock instances, we get a duration object returned. So I'll wrap this operation in parentheses to encapsulate the duration in it. Then to get the actual seconds of the duration, we can call the seconds method of it. Okay, we loaded the result message. Now it's time to pass it off to the goal handle to send the result back to the client to tell it that the action succeeded. And then for clarity, I will print out that the goal succeeded. Oh, and it seems I forgot my semicolon right here, so I'll be sure to put that in. And that gets rid of our errors that we had. All right, that's about it. We now have an action server. So if I scroll to the top, we created an action server node, which keeps track of the robot position via a subscription. And when we receive a goal, we will handle that goal, in which we will accept and execute it. And then in our handle accepted statement, we call our execute method in a separate thread to prevent blocking. And in this callback function, we calculate the distance between the goal point and the robot position in a loop until we get close enough to the goal point that we send back a result with the elapsed time. One last thing I will do is put another cout statement in our constructor to let us know when the server is running. Now that was a lot of coding, so let's save this file and configure our cmakelist.txt file. Be sure to include all the action dependencies and the CPP type support for the custom action interface. Oh, and I just realized I forgot a dependency, which was our ROS client library actions dependency. Let's save it and start the compilation. All right, so it compiled successfully. So I'll go ahead and close this. Alrighty, so I'll go ahead and minimize this. And I'll go ahead and clear the screen of our source terminal, and I will start up the action server. So we see that the server started. Now let's go ahead and pull up the ROS status screen in our VS Code. So I'll hit F1, type in ROS status, and we can hit ROS show status. Go ahead and minimize this for right now. So it actually shows as offline for right now. All I have to do is run ROS to node list, and sometimes that'll force the daemon to start up if it hasn't already. So there we go. We have our navigate action server node, and we see some topics related to our action, as well as some services. Now, this is a feature I actually really enjoy about this extension, is because some of the information would have been hidden to you if you used the terminal commands. So for example, in this second terminal tab, I'll go ahead and clear the screen, and I'll source it. And then I can go ahead and run ROS to topic list. And we don't see the feedback or status topics like we do within VS Code, right? So we don't see this navigate action status or navigate action feedback topics. And that's because these are hidden topics. So if I instead pass in the -- include hidden topics flag, which you can do with tab completion, we get a full list like we see in VS Code. Now the reason these are hidden are because these are part of the action, so it should only really be interacted with through an action client, but hopefully you can see in action is just a series of services and publishers. When we send the goal, behind the scenes it's really just a service call like we did in the last couple lectures, and the feedback is just a publisher. Okay, so sorry if that seemed off topic, but I feel like that is worth noting so you better understand how actions operate behind the scenes. Now let's actually go ahead and create our action client. We could do that in another C++ file, which we will do in a bit, but for now, let's just use the ROS2 action commands. And for now, I will go ahead and move this up a little bit. First up, let's list our actions, since that is one thing our VS Code status page doesn't explicitly do. So here we see our navigate action, which we declared in our server. Then I will call ROS2 action send a goal to send a goal to our server. As always, you can use tab completion to see more options. So if I go ahead and do that, you see we can call these flags as well as the action name. I will actually use the feedback flag, which will print the feedback to the terminal and specify the navigate action. Then as usual, I can hit tab twice and we see we need to provide the action type, which in this case is our navigate action. Then I can double tap again and we see the goal point request. So I can start typing it. Now here it formats it in the YAML format, which in my personal opinion is terrible for use in the terminal. As you will quickly see, if I change these values in the terminal to say 110 and I hit enter, we actually get an error because it didn't get formatted properly in the terminal, which is really annoying. So what I will do is clear the screen, then I will hit the up arrow, and here we see it formatted with no spacing. I will go ahead and wrap the expression in double quotes. Then I will put a curly brace after the goal point to encompass X, Y, and Z. Then last but not least, we can remove all these silly slashes which were used for the terminal formatting and instead separate the X, Y, and Z attributes with commas. So if I go ahead and stretch this out just a little bit, we can see the full message. So now if I hit enter, we see it waits for the server, then we see the feedback start printing out our terminal tab with the client. Above in the server terminal, we see it receive the goal point as we configured it. And we see the feedback is indeed the distance 110 would be from 000, which is where our robot position was initialized at. So that's why we get this 1.41. So the last thing we need to do is have the robot move to that goal point. We can simulate that by quickly creating a publisher using the command line interface in another tab. So for example, I can say that the robot moved to position 100 and I specified the once flag so that I only publish a single message. And here we see the feedback update from 1.4 to 1. So I can go ahead and put us within the threshold distance of the goal with this next published position. And here we see the feedback changes once, and then we get returned a result because we are within the threshold distance, so we get returned the elapsed time in our client terminal. And over on the server, we see that the goal succeeded. Well, congratulations! If you made it up to this point, you successfully implemented your action server to take in a goal, provide feedback about how far away our fake robot was away from a goal point, and then we got the result of the elapsed time. Well, congratulations! If you made it up to this point, it means you successfully implemented your action server to take in a goal, provide feedback about how far away our fake robot is away from that goal point, and then we got the result of the elapsed time. So to wrap this lecture up, we'll be creating a client node to communicate with our action server rather than using the terminal commands. So I will go ahead and stop our action server for right now and head back over to VS Code, where I will go ahead and close our ROS2 status bar for right now. open up our File tab, and create a new file in our source folder called action_client.cpp. I can go ahead and include the inclusion statements and the type defs at the top of my code from before in the server. I can also go ahead and copy my main function from my server code and paste it into my client code and just change the name of the node class to Navigate Action Client Node. Then I'll create the class above. As usual, this will inherit the functionality from the node class. Then I will go ahead and create our constructor. Then I can create a client pointer variable. So I grab the client class from the RCL action library and set it as our navigate action type. Then I can initialize this client using the create client function. This will take in the node object and the name of the action, which in this case is navigate. Now we can use this client to interact with our action server. For now, I will go ahead and create a function which prompts the user for the goal, which will get called within this constructor. So we'll go ahead and define it in my private scope. The first thing we will do is prompt the user for the X, Y, and Z coordinates for the goal point. So I will initialize a goal message and do a series of cout and cin calls to prompt the user and take an input for each coordinate. Then once we have the goal data loaded, we will wait for the action server to be live. Then once it's ready, I will prompt that we are sending the goal. Alright, now before we go ahead and send the goal, we will actually set up a goal options object like so. What this goal options object allows us to do is specify callbacks to run when we receive a response that the goal was accepted or rejected, when we receive feedback, and when we finally receive the final result once the goal is finished being processed. So first up is the goal response callback. It'll take in placeholders, so it can take in the goal handle future object, so I'll declare the use of placeholders above. So now we need to define this callback function, which I can do below. Oh, and it seems I made a mistake when I copied over my imports from my server. I want to change this type def here from server goal handle to client goal handle. So I will keep it as the goal handle object, but this time we'll be referencing the client goal handle object, which has some different attributes to it. Now, since this goal handle acts like a future object, I need to call the get method on it. Now, there are a couple things we can do with this goal handle, such as get the goal ID from the server, or the timestamp the goal was accepted, as well as some other options. For now, all we need to do is verify that we even got returned a goal handle, which will signify that the goal was accepted. If not, we know the goal got rejected by the server. Great, and that's all we'll do for now. Now let's head back to the send goal options and declare a feedback callback to process any feedback coming in from the action server. So now I can declare this callback function, which takes in two arguments: the same goal handle future object as our goal response callback, as well as the message received from the feedback publisher. Now you can do the same things you could do with the goal handle as earlier. You could get it and do something within your feedback callback, but for now I won't use it. So I will just void it out so I don't get an unused variable warning when we compile, and just print out what the feedback distance to point is. Alright, with that feedback callback out of the way, now I just have to declare my result callback, which I can go ahead and declare from my options above. And of course, I will go ahead and define this below. In this case, the input argument received is a goal handle wrapper result object. So here we could just print out the elapsed time, which I can do like so. Now this may seem a little funny since I had to call result twice. Well, that's because this wrapped result object also contains some other information such as the result code and the goal ID. So some people like to use this information to assess that the goal got processed successfully. So for example, you could use a switch statement to cover the various different possibilities of what could have happened to our goal as it was being published. So for example, if it succeeded, then we can grab our print statement, put it here within the case statement, and break out of this case loop. Then I can add additional cases, such as in the case our goal got aborted or cancelled. There is also an unknown enum for this result code. So for that, we can just make a default function in case we got unknown or some type of response we don't know how to process. Then I can go ahead and shut down this node regardless of the result to stop the spin function and close out the node. Great, with that we finished our goal response callback, so that the last thing we need to do is go back into our function where we define our goal options and actually send the goal to the server, which we can do with the async send goal method of our action client. This will take in the goal message we loaded earlier and the goal options which we specified all our callback functions on. Alright, and that about covers it. We created this node which defines an action client. We then went ahead and prompted the user for the X, Y, and Z coordinates, then defined our send goal options, which has 3 separate callbacks to process the goal response, the feedback, and result. Then we send the goal to the server. So with that, I will go ahead and save this file and head over to our cmakelist.txt file. As usual, we will go ahead and add our executables. And add to our install targets list. So with that, I'll go ahead and save our cmakelist.txt file and recompile our project. Oh, and I used the wrong function here. I meant to send goals. So if I actually go back into this, so if I call async send goal, goal message, and our goal options. All right, let's try this again. I'll go ahead and save the file and recompile. All right, and that did the trick. So I'll go ahead and close this and head over to our terminal. Go ahead and clear some of these screens. And first off, I will start our action server. Then I can go ahead in the second terminal tab and call the action client node. And here we get prompted for the X value, so I'll just put in 1, then hit enter. Then I will do 1 for Y, and I'll do 0 for Z. So we see our goal got accepted by the server, and now our feedback is being published by our client node. So I will go ahead and move the robot closer to the goal point by using our publisher command from earlier. So in this case, I'll move it to x equals 1, and so we see our feedback changes. And I will go ahead and put it even closer like we did last time so that we are close enough for the threshold. And we see we feedback updates one last time before printing out the result. Oh, and it seems I made another typo here where I actually had this nested in the default stage. So I'll go ahead and modify that really quickly, put it outside of the scope of our switch statement, save it, recompile it. And for the process of retrying this all out, clear this, restart our server, restart our action client. I'll put in the same values. We get our feedback, and I will set us to go close to the point. So we meet our distance threshold, and there we go. Now it actually worked successfully, where once we got our result and printed the results, we exited out of our node successfully because of that ROS client library shutdown command at the end of our result callback. You can feel free to continue more requests. So for example, now I can travel back to the origin. And so here we see it's still collecting goals, even though we've already processed them. And so I can go ahead and update our new robot position like so. And we see it still works. All right, that was a lot to take in, but here we have successfully implemented a ROS action in which our client sends a goal point and the server subscribes to the robot position to calculate the distance, which it sends as feedback. And then finally sends a result of how long it took to complete that action. In this case, we just manually changed the position of the robot to get closer to the point. But surely you can see how this ROS action framework can be applied in real life, such as commanding a robotic arm to pick up a particular object and place it somewhere. In this case, your goal consists of an object for the robot to pick up and the location to place it. Then within your server command, the autonomous code to actually make your robot do the action, all the while publishing feedback such as the status of the job, and eventually receiving a result summary if the job was completed successfully or not. But nonetheless, congratulations on implementing your very own ROS2 action.